Carbocations are a cation of carbon. That is, when a carbon is bearing a positive charge, we get a carbocation, cation of carbon. That is, it is something like this one, C positive. When we talk about this C positive, so looking at it, so we can find there are 3 sigma bonds, number 1, number 2 and number 3. So it has 3 sigma bond. With these 3 sigma bonds, each associated with 2 electrons, therefore we can say it has 6 electron in total. So it has 6 electron. That means, since incomplete octet, therefore we can say this is electron deficient. So we can say this is electron deficient. And if this is electron deficient, so it must be an electrophile. So it's an electrophile. It's an electrophile. So these carbocations are electrophilic in nature, having 6 electron, incomplete octet, it is electron deficient. So these cation of carbons are called carbocation, which are electron deficient or electrophile. The second and very important aspect of this carbocation is its structure. That is, its structural feature is very important to understand, because many of the reactions and their stereochemistry depends on the structural feature, and therefore looking at it, we can see, if we just apply this, so based on this number of sigma bonds, we can say it has 3 hybrid orbitals. So it is sp2 hybridized, and since it is sp2 hybridized, therefore it has planar structure. So if we draw its structure, so we can easily see here, like the carbon, here is the carbon with this 1 bond, 2nd bond and the 3rd bond. So all these are lying in the same plane, and therefore we can show them like they are lying in the same plane, and here it is. So it is lying, all the 3 carbons are lying in the same plane, and one more p orbital which is vacant with this is lying here, like it is present in the perpendicular plane like this. So this carbocation has something like this structure. If we try to put its structure in a wedge and dash diagram, then we can see here it appears like this carbon, and here is the another bond like this. So we can see here the second one edge like this one, third one is lying in the plane, shear edge lying in the plane, and the empty orbital or the vacant orbital is lying in the perpendicular plane. And so this is what the basic structure of carbocation, so having a positive charge. So this is C positive, or this is the structure of carbocation. So this structural feature is very important, because if the reaction, while considering the reaction, so it is affecting the stereochemistry of this carbocation. Now this is what the structural feature. If I look at its stability order, so we can see here its stability order. As we understood that these carbocations are electron deficient, therefore stability order would be enhanced or would be increased if we add some electron releasing group. So stabilized by electron releasing groups, ERG. So this electron release may take place either by means of plus I group, and that means this plus I group will increase the stability, or maybe it is a plus H like hyperconjugation, or it may also be a plus M or plus R group. We mean here plus M or plus R group means it is mesomeric and this is resonance. So carbocations are stabilized by plus I, like we already have seen, like CH3 and all, CH3, or we can say here it is O minus or something like that. So that kind of group. This is directly proportional to the number of alpha hydrogen. This is dependent on the filled p orbital, in conjugation with carbocation. Same applies for this plus R as well. So based on this we can easily see here and we can identify, like if we have to compare the simple carbocations, so we can find here the order would be like if we have CH3 positive, then another is CH3 CH2 positive, then we may have CH3 CH3 positive, and one H is here, and we can have this as well, CH3 CH3, and one more replacing this H by CH3, and then there is a positive. So looking at it, we can find there is no alpha hydrogen, 0 alpha hydrogen. In this case, in the second one, we can see that there are in total 3 alpha hydrogen. In the next one, we can see like this is 3 and here is 3. So total number of alpha hydrogen is 6 alpha hydrogen. And in the next one, we can see here, like in this case, there are 9 alpha hydrogens. So this is on the basis of hyperconjugation. On the other way around, we can also explain this using plus I or inductive effect as well, because in this case this is CH3, one of the CH3 group, which is showing this plus I group or plus I effect. In this particular case, there are 2 different methyl groups present, which is together adding to this plus inductive effect. And in the third case, we can see here, like in this case 1, 2 and 3, so 3 methyl groups are together giving plus I effect. So the intensity of maximum plus I effect is expected in the fourth one, whereas it is just less than that, it is in third, and then it is second, and the least in this CH3. Therefore we can say the stability order should be, so the stability order would be we can say, if I just number this like 1, this is 2, this is 3, and this is 4th, so we can say the order would be 4, then 3, then 2, then 1. So if I just look at the structure of this carbon, so this is your tertiary carbon, this is tertiary or 3 degree, this is 2 degree, this is 1 degree, and so we can also write it like this. It is 3 degree, then 2 degree, then 1 degree, and then it is methyl. This is applicable when we are considering only plus I effect and with the similar alkyl groups. Now let us have a look in which there is some kind of resonance or the other effect which is applicable. Like if we have this kind of structure, like considering this CH2 or CH3, CH double bond, CH2 positive. So this CH2 positive is stabilized by resonance, and therefore in this particular case there is enhanced stability. So we can say, if we compare this with this one, like CH3, CH2, CH2 and CH2 positive, so since it is stabilized by resonance, so we can say this is more stable than this one. So we can see here like the ordinary carbocations and the resonance stabilized system, so these are more stable, and based on this, if we have to compare, suppose this one CH2 double bond CH, CH2 positive, and if we have to compare this one like O minus CH2 positive and one more like this OH CH2 positive. So out of these three we can easily see what would be the stability order. Basis this, we can say this is having a pi bond, here it is a negative charge, and here it is the lone pair. So this is the kind of difference this molecule has, or these ions have. And so out of these three, if we have to compare which is more easily available for donation, so we can normally correlate, or we can easily correlate that since bonded pair of electron is less available in comparison to the simple or free non-bonding electron pair, or it is less available than the negatively charged species, and so the order would be, therefore we can say the order would be like this. So in this particular case, the third one is, if I just number it like 1, 2 and 3, 1, then 2, then 3, so we can say 2 is more stable, then it is third, and then it is first. So this is some of the examples which can easily be explaining the stability order of carbocation and its structure